Hello and welcome everybody to my presentation on our paper Evolutionary Minimization of Traffic Congestion. This work is based on the bachelor thesis of Leon and myself, and we were advised by Philipp, Louise, Martin and Tobias. I'm glad to present our work here at GECCO today, so let's dive right into it because we think it's an important topic. We deal with traffic congestion, and of course, as a driver, if you drive a car, you know that it's annoying to be in a traffic jam. But street congestion and these traffic jams, pollution, they have been becoming increasingly large issues over the last few decades. In German cities alone in 2019, these effects caused additional costs of around $3 billion or euros. So you can already see the impact that traffic congestion has on our daily lives. And one way this was tackled in recent publications is so-called strategic routing. So you might be familiar with traditional routing problems. For example, you could consider the very basic shortest path problem a routing problem, where you want to route a single driver on the fastest route. You might also think about a vehicle routing problem or the traveling sidesman problem. You could also consider these routing problems. So what is a strategic routing about? Well, as Bläsius and others introduced, with strategic routing, we consider routing flows of traffic. So we do not want to route a single driver, but we want to route multiple drivers. So like 500 drivers, 1,000 drivers. How can we split the traffic up optimally, for example? And we also want to respect how drivers psychologically behave. And we might propose more routes, so it's like a more real world application. But at the core, it's that we want to route multiple drivers, and we want to do a shared scoring. We want to have a social view and not an individual egoistic point of view. And one problem that they introduced, or the core problem that their paper introduced, is the so-called single alternative path problem. And in this problem, we are given a graph and an original route from S to T. And now we want to find the optimal alternative route, depicted here in orange or red, where the two routes overlap, such that if the drivers split up onto these routes, their overall travel time, for example, is minimized. You could also consider other target functions here. And for our work, we first went ahead and generalized this problem to the so-called multiple routes problem, because if you think about it, we still here, for the multiple routes problem, get this graph, but we lift the restriction of the original route. So for the multiple routes problem, we want to find n routes, and in this case n equals 2. And here you can already see maybe the original route here was the shortest path, but now our alternative route here is forced to overlap with the original route, which might become worse overall. So maybe it might be better if we just propose two routes and are not bound to a given original route, like here, that we can make them completely disjoint and therefore get a better traffic distribution, unlike the SAP problem does. So both are NP hard, so it's not very straightforward to calculate a solution, and this is why we want to deal with this using evolutionary algorithms. But first of all, we need to think about if we actually calculated a set of routes in the multiple routes problem, for example, how do the drivers split up? And in a nutshell, a psychological model does tell us exactly that. So given a set of routes, here these two routes on the graph, we ask the psychological model how the drivers would split up. So here maybe two drivers would use this route and one driver would use this route. And this flow that the psychological model should output should be valid. What does this mean? Well, again, consider a flow is a distribution of drivers or drivers per unit of time onto the graph, or more to be more precise, onto the edges of the graph. So the flow should respect that we should only route k drivers, so it basically should be within our problem constraints, and also we should only use the n routes that the psychological model was given. The psychological model is not allowed, if we beforehand wanted to score these routes, to somehow use this unused edge here. And for our case here in this talk, we will consider the n-user equilibrium, which is basically, if you know the user equilibrium, it appears in certain contexts where everybody does selfish choices and they reach a certain state. And for us, we want a user equilibrium where the drivers achieve on this limited set of routes. And this, I'm not going to discuss the mathematical details here. It's not as straightforward to calculate this. So we approximate it using a convex program and solve it with the so-called Frank-Wolf algorithm. So this is important when, for example, trying to score a set of roots in a evolutionary algorithm. And then, as soon as we know how the drivers are distributed, we can actually evaluate our fitness function. So we want to minimize the overall travel time, so the time all drivers need to traverse the graph given our route set. And this can be calculated by using a real-world graph, real-world information. How long, for example, do 100 people take to traverse this highway? This we know by real-world data, and this enables the evaluation of the fitness function. So, to sum up the problem, we want to find n routes from S to T, such that if k drivers form an n user equilibrium on them, the overall travel time is minimized. This is what our algorithm looks like. If you're watching the video afterwards, feel free to pause. But in a nutshell, we have an evolutionary algorithm with a population, and each individual of the population is a root set. And each individual then again contains n roots, because we have multiple candidate solutions. So each root set is a candidate solution. We have multiple candidate solutions, and then each candidate solution has to contain n roots. And basically we need randomness in an evolutionary algorithm. For this, we employ a randomized Dijkstra algorithm, so shortest path algorithm, where we basically, during the relaxation from the queue, we really randomize the edge weights a bit and perturb the edge weights, such that each run of the Dijkstra algorithm actually does give us a little bit of randomness with respect to the travel time. And this enables that we have like a diverse set of routes at the beginning, and then, while of course we have some kind of loop while termination criterion is not met, and we do crossover. So this means we have to imagine that we take two root sets out of our entire population, and then we have n roots. So maybe we take n and a half roots from the one root set and n and a half roots from the other root set, join them together, and then have a new root set that is basically the merge of two other root sets and check if it's better. So this is crossover, and then we also clone like the parent generation, and then for mutations we basically mutate each clone of a parent individual, and we apply different mutation operations that I will discuss in a second. And these are also weighted, so we have like also each individual is therefore like modified a bit differently. And then we also check for a crossover individuals if they provided an improvement, and if they didn't provide any improvement, we throw them out again. So we only use crossover if it actually makes something better. And then we do a selection. So we take all the best individuals from our crossover individuals, our parent generation, and our mutated generation. So like a pretty straightforward evolutionary algorithmic structure. How do our mutation operators look like? Well, first of all, for global changes, we use the new root operator. So again, this is applied to a single individual or root set. So we remove one root of the root set, one of the n roots, throw it out, and so whatever progress we might have made there, we throw it out, and then just calculate a new randomized root again. So maybe we had this root, we throw it out and replace it by this root. We also want to make local changes, and we have two variants for that. We have the random p and link WP operator, and basically both of these select two vertices on one root, and then just recalculate the subsegment randomized a bit again with the random Dijkstra between these two vertices, and they differ basically in their selection of the two vertices. The third mutation operator that we have is the so-called X segment, and for this we need a more complicated example. So imagine that we have the blue root and the orange root. So the blue root is here, the red is again overlap, so the blue root goes here, 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 orange root goes here, 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 here. And now we can already see that they share the segment here, and what we could do is keep the blue root from here to this vertex, and then swap this shared segment. So you can see, think about if you have overlapping segments, multiple overlapping segments between roots, can basically exchange the sub-segments between these roots and try to get improvement out of this. So maybe it's better for all these cars that after here follow this route to also go here. And yeah, again, we see that these operators consider one of n roots because we modify a single root, and they might improve because we randomize our solutions. And this needs two roots because we basically want to exchange subsegments between roots. And this doesn't include randomness, but given the solutions we already have, we want to find out if they maybe can provide something better. So let us now discuss the crossover again. And for the crossover, to recap, we have two root sets, so two individuals, and then we want to take roots out of these individuals. So here in this case we have n equals 2. So we have two roots, and then we basically take here one root, the orange root from this individual, and the red root from this individual, and form a new individual that's basically the merge of these two individuals here. So the question is, how do we choose the roots from the individuals? And for this we employ a similarity measure, which basically measures how equal are, for example, the orange and the red root. And we now have different options to deal with this, so we could basically try all 2n over n possibilities, and then check which has the best heuristic here, so which are the most dissimilar. We could also greedily maximize, so we take like one root from here, then another one, so on, and try to get as dissimilar roots as possible. And we could also do this with a bit of randomness, because we might want to not only do this greedily and have some form of randomness within that. And so again, we want to force our roots to be a little more dissimilar, because probably having dissimilar roots will lead to a better split up of traffic. I'm not going to discuss this in much more detail here and refer to the paper for the rest. So we could rather take a look at some visual intuition, and basically here you see how the algorithm behaves for a route from Potsdam here to outer space of Berlin, basically. So we want to calculate multiple routes. We can already see at the beginning that we have like similar routes, like using the Autobahn here, and then now the algorithm tries out like different options of going through the city. Also does some local optimization here. So you can really see that the algorithm is trying out like different stuff, continuously optimizing the overall traffic time, trying out like local optimizations, larger subsegments, smaller subsegments, and this is basically the visual intuition of how our algorithm performs. And to continue with the next slide to discuss some results, and we want to especially discuss the mutation operators. So you can see a box plot here, and basically in our paper we consider 11 different scenarios. Each scenario is a bit different. So we have short inner city routes, we have longer routes that you use the highway, for example, and we want to check how the algorithm performs by gradually introducing our mutation operators. So we start with RP only, which is just like local changes. Then we introduce the new route operator here in the orange box. Then we introduce the smarter choice of local changes, where we enforce rerouting to shared segments, so to traffic light crossings, for example. And then at last we introduce the exchange segment operator. And what's important, that like really the new route operator has statistically significant, using a Mann-Whitney test, impact. You could, for example, see this here in scenario 9, where introducing the global new route operator really improves not only the outliers but also the median quite a lot. So this is the reason you should always consider global changes within our evolutionary algorithm. And overall, we can see that all mutation operators provide some kind of impact. And note that the scores here have been normalized because, of course, the travel time is different between all these 11 routes. And last, I note that the impact of the population size is also significant. And here we only use the single individual. So we also have taken a look at the single alternative path problem, and compared to the highly tailored solver, our algorithm achieves 99.69% of the quality of their exact solution. and requires only 40% of the runtime, which is not surprising because even though their Taylor solver is optimized and highly tailored to the problem, our algorithm is a heuristic for an NP-hard problem, and they use graph algorithm engineering techniques to find a solution. And it's promising that we are like better than them, because we can apply this now to different strategic routing problems in the future, and we believe this is a great step forward in the strategic routing research that we made here. So with that, we conclude, or I conclude my talk, and thank you very much for your attention. If you have any questions, I'm very much open to discussing them with you at the conference and also via email here. Feel free to contact me, and thank you very much for your attention again, and see you and goodbye.